Something invisible is pulling our galaxy through space at incredible speed. This is the Great Attractor, a colossal gravitational mystery hidden in plain sight. By the end of this journey, you will understand the fundamental forces quietly guiding our cosmic path. We will explore how astronomers discovered this anomaly and what its immense presence means for our long-term journey. Where is it drawing us, and what does its existence reveal about the vast, unseen architecture of the universe? What hidden truth about the cosmos most captures your imagination? Our galaxy is not drifting aimlessly. It is racing through the void at over 2 million kilometers per hour, caught in a cosmic current it cannot escape. This baffling motion first became clear to astronomers not by looking at a single star, but by observing the collective drift of entire galaxies. In the grand tapestry of the universe, where everything is supposed to be moving apart from everything else, a peculiar exception emerged. Whole swaths of galaxies, including our own Milky Way and its neighbors, were all streaming together in the same direction, like leaves caught in a powerful, unseen river. This phenomenon, a coordinated drift on an almost unimaginable scale, was given a name: bulk flow. It was the first major clue that the universe's expansion was not the only force guiding our path. The hunt for the source of this motion intensified through the 1970s and 80s. Using radio telescopes to pierce through the veils of interstellar dust and painstaking galaxy redshift surveys to map velocities, astronomers traced the flow back to a specific part of the sky, the direction of the Hydra Centaurus superclusters. But the calculations did not add up. The sheer speed of our galactic journey demanded a gravitational anchor of staggering proportions, a concentration of mass that should have been impossible to miss. Yet when they looked, they saw nothing matching the force they were measuring. The visible galaxies in that region were simply not enough to account for the pull. This was the core of the mystery, a gravitational signature without a visible source. How could something with the mass of tens of thousands of galaxies remain completely hidden from our view? The answer lay in an obstacle we had been looking past for our entire history, the very heart of our own galactic home. Our own galaxy was hiding the very thing we were searching for. The core of the Milky Way, that brilliant and crowded band of light we see stretching across the night sky, forms a thick, obscuring wall. For astronomers trying to peer beyond it, this region presents a profound challenge, a cosmic blind spot known as the Zone of Avoidance. Nearly 20% of the universe outside our galaxy is completely blocked from our optical view by an immense concentration of stars, gas, and cosmic dust. It was like trying to find a distant mountain range while standing in a dense, luminous fog. The Great Attractor lay directly on the other side of this celestial barrier. To solve the mystery, we needed to find a way to see through the fog. The solution was to stop relying on visible light and instead listen to the universe with different ears. Astronomers turned to other wavelengths of energy that can slip through the interstellar dust almost unnoticed. Infrared light, which we feel as heat, can penetrate these clouds. X-rays emitted by incredibly hot and energetic objects also shine through, and radio waves, a much longer wavelength than light, travel unscathed. Pioneering satellite missions like the Infrared Astronomical Satellite and the ROSAT X-ray Observatory began to map the hidden landscape. They revealed a stunning reality. Behind the veil of the Milky Way lay not an empty void, but a bustling metropolis of previously invisible galaxies and enormous clusters of stars. The Great Attractor was not a single, colossal object waiting to be found. The gravitational pull we were feeling was the collective tug of an immense concentration of mass, a vast supercluster of galaxies embedded within the even larger cosmic web. Peering through the zone of avoidance did not simply reveal the source of the pull, it unveiled an entire hidden continent of the universe, a realm of structure we never knew was there. Deep within the gravitational heart of the Great Attractor lies a true titan, the Norma cluster. This is not a single galaxy, but a dense swarm of them, hundreds strong, all bound together in a cosmic dance by their collective gravity. Think of it as a bustling metropolis on a scale that defies comprehension, located some 200 million light-years away. The total mass locked within this cluster is staggering, thousands of times greater than the entire Milky Way. For a time, this seemed to be the answer, the primary engine of the mysterious pull. Our view of this colossal structure was pieced together using X-ray eyes like those of the Chandra satellite. These instruments revealed a vast, shimmering atmosphere of superheated gas enveloping the entire cluster. This gas is not just a cloud, it is a direct measure of the cluster's immense gravitational power, a deep well of potential that tugs on everything around it, including us. The Norma cluster was the central anchor we had been searching for, a significant piece of the puzzle finally falling into place. Yet the numbers still did not add up. Even with the staggering mass of this galactic congregation, the math insisted that something even more massive was contributing to our motion. The discovery of the Norma cluster was a monumental breakthrough, but it also served to deepen the mystery, revealing that the true source of the cosmic river was far grander than anyone had initially suspected. But the gravitational story did not end with the Norma cluster. The true scale of the force pulling us only becomes clear when we look far beyond it, to a structure of almost unimaginable proportions known as the Shapley Supercluster. If the Norma cluster is a bustling metropolis, Shapley is an entire continent of galaxies, the single largest concentration of mass we have yet found in our observable cosmic neighborhood. It lies a staggering 650 million light-years away, a distance that humbles the mind, and it contains dozens of massive galaxy clusters, all bound together by their collective gravity. The sheer weight of this region creates a profound impression in the fabric of spacetime, a gravitational basin so deep that it influences the motion of galaxies across an immense volume of the universe, including our own. Detailed galaxy surveys and observations of how its gravity bends the light from more distant objects have confirmed its overwhelming influence. This discovery prompted a dramatic shift in our understanding. Some scientists now argue that the Shapley Supercluster is not just a contributor, but potentially the primary engine of the great cosmic river we are riding. From this perspective, the Great Attractor itself, with the Norma cluster at its heart, is not the final destination. It is more like a major waypoint, a local swelling in the current, caught within the far grander pull of Shapley's immense gravity. This reveals a fundamental truth about the architecture of our universe, a hierarchy of structure where galaxies form clusters. Clusters gather into superclusters, and these superclusters themselves define the largest currents in the cosmic flow. The Great Attractor is not a solitary anomaly. It is one powerful feature within a vast, dynamic system, a system whose full extent and influence we are only just beginning to map. To truly grasp the power of the Great Attractor, we must pull back and see the universe in its entirety. This is the cosmic web, the fundamental architecture of everything. Picture the universe not as a random scattering of galaxies, but as a colossal sponge, a vast network of interconnected threads. These are the filaments, immense highways of dark matter and galaxies stretching across billions of light years. Where these filaments intersect, they create dense nodes, the superclusters, which act as gravitational anchors. The spaces between them are the voids, immense and nearly empty deserts of cosmic space. Within this grand design, the Great Attractor is not a singular, mysterious object. It is one of these nodes, a major crossroads in the cosmic web where the threads of matter converge, creating a gravitational well so deep that it draws entire galaxies inward. Our own home, the Milky Way, resides within a single leaf of this structure, a supercluster we have named Laniakea, a Hawaiian word meaning immeasurable heaven. This vast structure, over 500 million light-years across, is our true cosmic address, and at its heart, one of its primary gravitational centers, lies the Great Attractor. So our journey is not toward a single point, but along a filament, a preordained cosmic highway flowing toward a regional hub. This entire framework is the predicted outcome of the universe's own evolution. Powerful computer simulations, based on our understanding of dark matter and dark energy, show how it all began with the tiniest of ripples in the fabric of the early universe. Over billions of years, gravity amplified those ripples, pulling matter into the web we see today. The Great Attractor is simply one of those original dense patches grown to immense scale. This shifts our entire perspective. We are not being pulled by a hidden force. We are riding a universal river system, flowing down gentle gravitational slopes toward the mass concentrations that form the continents of the cosmos. What other invisible currents might be guiding the fate of galaxies we cannot yet see? This unseen river of gravity has a hidden source. The immense pull of the Great Attractor is not generated by the galaxies and superheated gas we can finally observe. A significant portion of its power comes from something entirely invisible, a mysterious substance known as dark matter. Think of it as the universe's hidden framework. We cannot see it, touch it, or directly measure it with any telescope because it does not emit, absorb, or reflect light. Its presence is revealed only through its persistent gravitational influence. In fact, dark matter makes up about 27% of the entire cosmos, a quiet, dominant partner to the ordinary matter that forms stars, planets, and us. Without it, the universe as we know it would simply not hold together. Around every galaxy, including our own Milky Way, dark matter forms an immense, diffuse halo, a vast sphere of invisible mass that extends far beyond the galaxy's visible edge. It is this halo that provides the extra gravitational cohesion, the force needed to explain why galaxies spin as fast as they do and why clusters of galaxies remain bound to one another. In the region of the Great Attractor, models suggest these dark matter halos are not isolated. They overlap and merge, creating vast, interconnected reservoirs of invisible mass that amplify the gravitational influence far beyond what the visible stars and gas can possibly account for. The true scale of the attractor remains hidden from our eyes, its full mass only inferred through the quiet, steady pull it exerts on everything around it. To truly understand the forces guiding our cosmic journey, we must uncover the nature of this invisible component. Deep underground, in laboratories shielded from cosmic rays, experiments are running in an attempt to catch a fleeting glimpse of a dark matter particle. Success would be a revolution, finally revealing the identity of the substance that shapes the largest structures in the universe and powers the great attractors that guide us through the void. For now, this invisible hand remains the central mystery, a fundamental force woven into the fabric of space itself, compelling us to look deeper into the unknown to understand our place in the light. Our journey through the cosmos is not a simple, uniform expansion. Each individual galaxy has its own unique motion, a personal velocity superimposed on the grand backdrop of the universe stretching outward. Astronomers call these deviations peculiar velocities, and they are the direct fingerprints of local gravity. The Great Attractor creates one of the most significant of these anomalies ever detected. Our own Milky Way, for instance, is not just passively riding the Hubble flow. We are being actively drawn, adding a peculiar velocity of roughly 600 kilometers per second directly toward this hidden concentration of mass. To measure such a precise motion across such vast emptiness requires extraordinary tools. Astronomers rely on what are known as standard candles, celestial objects with a known intrinsic brightness. By comparing how bright these objects appear to us with how bright they truly are, we can calculate their distance with remarkable accuracy. Two of the most trusted standard candles are Cepheid variable stars, whose rhythmic pulses reveal their true luminosity, and the immense explosions of Type 1a supernova, which always shine with a consistent peak brightness. Major sky surveys like the 2-micron All-Sky Survey and the Sloan Digital Sky Survey have used these cosmic lighthouses to meticulously map the motions of millions of galaxies. Their collective data paints a vivid picture of a vast river of galaxies, all streaming in concert, revealing the attractor's gravitational influence stretching across millions of light years. These peculiar velocities are more than just measurements of motion. They act as a form of cosmic scale insight, allowing scientists to weigh the unseen. By observing how much a galaxy's path deviates from the smooth expansion, astronomers can calculate the total mass of the invisible structure pulling on it, even if that structure is completely shrouded in darkness. This method confirms that the Great Attractor's true mass far exceeds the sum of its visible parts. The study of these gravitational anomalies does more than just confirm an immense unseen presence. It provides a critical testing ground for our fundamental theories of gravity and for our models of how the largest structures in the universe coalesced from the primordial soup. It forms a crucial bridge connecting what we can directly observe with what our theories predict must be there, guiding us toward a deeper understanding of the hidden architecture that dictates our cosmic journey. The universe is expanding, but not in a perfectly uniform way. Imagine blowing up a balloon with tiny dots on its surface. As the balloon inflates, every dot moves away from every other dot. This is the essence of Hubble's law, the grand backdrop of cosmic expansion where a galaxy's speed away from us is directly proportional to its distance. In this ideal picture, our galactic neighborhood should be a sea of steadily receding islands. Yet we are not simply drifting apart. The Great Attractor introduces a powerful, local distortion to this elegant rule. Its immense gravity creates a regional sink in the fabric of spacetime, pulling galaxies inward and superimposing a new motion on top of the cosmic recession. Within a sphere of about 150 million light-years, its gravitational influence becomes the dominant force, compelling galaxies to flow toward it against the overall expansionary tide. This is why we measure our own peculiar velocity, that 600 km per second drift directly toward the hidden mass. It is a deviation from the Hubble flow, a clear signal that local gravity can and does overwhelm the universe's stretching on these scales. As we zoom out to view billions of light years, this local wrinkle smooths out and the majestic Hubble flow reasserts itself. But it is precisely these local anomalies that are so precious to cosmologists. They are like eddies in a great river, revealing the hidden rocks and contours of the riverbed below the surface. By studying the precise way the Great Attractor warps the motions of nearby galaxies, scientists can perform a kind of cosmic accounting. They can weigh the total amount of matter in that region, both seen and unseen, with extraordinary precision. This intricate dance between global expansion and local attraction is a cornerstone of modern cosmology. It illustrates a profound truth that the history of our universe is written in the tension between these two fundamental forces, the outward push of dark energy and the inward pull of gravity. The Great Attractor, therefore, is more than a destination. It is a natural laboratory. The data we gather from its influence on galaxy motions helps refine our most critical cosmic parameters, like the Hubble constant, which measures the rate of the universe's expansion. Each subtle measurement brings us closer to understanding the true density of the cosmos and the ultimate balance of power between the forces that shape our cosmic journey. The true nature of the Great Attractor remained a ghost on our star charts until our vision evolved. We learned to see the universe not just with light, but with heat and energy. This shift was powered by a new generation of eyes in the sky, space telescopes designed to perceive the invisible. The Spitzer space telescope, for instance, was an infrared master. Its detectors were tuned to the gentle warmth of starlight absorbed and re-radiated by cosmic dust, a wavelength that slips effortlessly through the veils that block our ordinary view. Meanwhile, observatories like XMM Newton and Chandra opened a window into the high-energy universe, capturing the fierce X-rays streaming from clouds of gas heated to millions of degrees. It was through these new senses that the hidden landscape finally came into focus, where our optical maps showed only a blank wall in the zone of avoidance. These instruments revealed a bustling port city of galaxies. Vast clusters, previously just gravitational phantoms, now appeared as brilliant, swirling clouds of hot, X-ray emitting gas, each one a clear beacon of immense mass. The 2-micron All-Sky Survey, or 2MASS, used infrared light to meticulously catalog millions of individual galaxies hiding behind the Milky Way's core, painstakingly filling in the blanks on our cosmic map. This multi-wavelength approach was the key to building a three-dimensional model of the Attractor region. By combining the infrared census of galaxies with the X-ray maps of their hottest gas, astronomers could finally weigh the entire structure. They saw how clusters were grouped into larger clouds, and how these clouds were connected by faint, filamentary bridges of matter, all contributing to the collective gravitational pull. The vague anomaly of the Great Attractor was gradually transformed into a detailed cosmic metropolis, its avenues and neighborhoods charted with increasing precision. This transformation was not just about finding more mass, it was about understanding its architecture. Each new dataset from these technological marvels refined our model, confirming that the pull we feel is the sum of countless parts, a complex gravitational field generated by an entire hidden sector of the universe. These breakthroughs underscore a profound truth in astronomy. Our comprehension of the cosmos is limited only by the tools we create. Every leap in instrumentation doesn't just show us more, it reveals a universe more intricate and interconnected than we ever dreamed. What other colossal structures might be hiding just beyond the limits of our current perception, waiting for the next revolution in how we see? So what does a hidden gravitational anchor of this scale actually weigh? The numbers involved are so immense they defy easy comprehension. Current models suggest the total mass of the Great Attractor complex is equivalent to tens of thousands of galaxies like our own Milky Way, all concentrated within a region spanning roughly 300 million light-years. To put that into perspective, picture gathering every single star, planet, and cloud of dust from tens of thousands of galaxies and compressing them into one unimaginably dense knot of cosmic influence. This staggering estimate is not pulled from thin air. It is pieced together through multiple, independent lines of astronomical detective work. The first clue comes from watching how galaxies move within its grasp. By measuring the peculiar velocities of thousands of galaxies, scientists can work backward, calculating the amount of mass required to generate such a powerful and coordinated flow. It is like watching leaves swirl in a pond and deducing the size and shape of the hidden drain pulling them inward. Another critical method involves a phenomenon known as gravitational lensing. The immense gravity of the Great Attractor acts like a lens in spacetime, subtly bending the path of light from even more distant galaxies that lie behind it from our point of view. By carefully measuring this distortion, astronomers can literally weigh the invisible mass causing it, mapping its distribution across the sky. These techniques all point to the same overwhelming conclusion. The visible stars and the brilliant clouds of hot gas we can now detect in clusters like Norma account for only a small fraction of the total pull. The dominant force, the true engine of this cosmic river, is the vast, unseen reservoir of dark matter that permeates the entire region. Some calculations converge on a specific, almost incomprehensible figure, a mass on the order of 10 to the 17th solar masses. That is a 1 followed by 17 zeros. Yet for all our advanced methods, a degree of uncertainty remains. The zone of avoidance still obscures a portion of the structure, and we are looking at a complex overlap of multiple clusters and filaments, making it difficult to disentangle exactly where one gravitational influence ends and another begins. This is not just an academic exercise. Refining this mass estimate is absolutely crucial. It allows us to test our most fundamental models of how dark matter behaves and how the cosmic web formed from the primordial universe. Each decimal point of precision brings us closer to understanding not just where we are going, but how the universe itself built the pathways that guide us. Our long-term trajectory is written in this gravitational flow. We are not heading for a single, dramatic convergence with the Great Attractor. Instead, our galaxy is riding a gentle slope in spacetime, flowing toward this regional hub as part of a much grander voyage toward the Shapley Supercluster. Think of it as a leaf caught in a vast river system, drifting first toward a local whirlpool but ultimately bound for the open sea. This journey is measured in billions of years. The distances are so immense that a close encounter with another major galaxy cluster is not in our future. We are part of a coordinated drift, a slow-motion rearrangement of the local cosmic web. For now and for eons to come, gravity is the dominant force guiding our path through this celestial landscape. Yet the universe is not static. A countervailing influence is at work on the largest scales, the mysterious presence of dark energy. This energy, woven into the fabric of space itself, causes the expansion of the universe to accelerate over time. As billions of years turn into trillions, this accelerating expansion will become the dominant narrative. The gentle gravitational slopes that currently guide our motion will be stretched and softened. The great cosmic flows, like the one we are riding today, will gradually slow, halt, and may even reverse as the spaces between superclusters become vast and unbridgeable. Our galactic journey is thus a tale of two forces, a temporary interplay between the local pull of gravity and the global push of expansion. We exist in a special era where we can still perceive these great currents and map the continental structures of the cosmos. This dynamic voyage invites a profound reflection on the future of all galaxies. Will they eventually merge into ever larger conglomerates, or will they be isolated islands forever receding from one another's view? The answer is written in the balance between the attractors that draw us near and the energy that encourages separation. The gravitational pull we feel is so immense that it has forced scientists to question the very laws of physics themselves. Could our understanding of gravity be incomplete? One compelling alternative, known as modified Newtonian dynamics or MND, suggests that gravity does not fade as quickly over vast distances as Newton and Einstein predicted. In this view, the strange motions of galaxies within the Great Attractor's realm might not be caused by hidden dark matter at all, but by a subtle change in how gravity itself operates on cosmic scales. It is an elegant idea proposing that we are witnessing not an invisible substance, but a new facet of a fundamental force. Yet for all its appeal, this theory struggles to fully account for the precise, coordinated flow of thousands of galaxies toward this specific point in space. The sheer power of the attractor's pull remains a formidable challenge for such modified gravity models. Other, even more exotic possibilities have been proposed. Could the universe be crisscrossed by cosmic strings, theoretical flaws in spacetime left over from the Big Bang that create immense gravitational trenches? Or perhaps primordial magnetic fields born in the universe's first moments imprint powerful irregularities that guide galaxies like ours. These ideas lie at the frontier of physics, and while they are not the mainstream explanation, they serve a vital purpose. They constantly test the foundations of our standard model of cosmology, pushing researchers to gather more evidence and refine their theories. The overwhelming consensus, supported by a wide array of observations from galaxy rotation to the cosmic microwave background, still points toward the existence of dark matter as the invisible scaffolding of the cosmos. But the enduring mystery of anomalies like the Great Attractor ensures that the scientific door remains open. It is this process of relentless questioning, of proposing bold alternatives and then subjecting them to the careful scrutiny of data, that truly drives our understanding forward. The attractor is not just a destination, it is a crucible for ideas, forcing us to look deeper and ask whether we have truly grasped the full picture of the universe's hidden rules. This immense cosmic force reaches far beyond the equations of astronomy, touching something deeply human within us. The Great Attractor serves as a powerful metaphor for the hidden currents that shape our lives, the unseen influences of history, culture, and connection that guide our paths just as surely as gravity guides the stars. We navigate our world with the confidence of what we can see and touch, yet so much of what truly moves us operates from the shadows, beyond our immediate perception. This idea has captivated storytellers and artists, inspiring science fiction tales of mysterious celestial objects with irresistible pulls and artworks that visualize the profound unknown. It has become a cultural symbol for the ultimate destination, the hidden truth, or the grand question we are compelled to answer. Philosophically, this discovery delivers a humbling message. It challenges any notion that humanity is the central character in the cosmic story. We are not passive observers in a universe designed for our benefit. We are participants, small and temporary, caught in the flow of vast, impersonal processes that began long before us and will continue long after. Our entire world, with all its complexity and beauty, is in motion toward a hidden point we cannot see, subject to forces we are only beginning to comprehend. This is not a cause for despair, but for profound wonder. The Great Attractor embodies the very essence of scientific curiosity, the drive to look past the veil and understand the hidden architecture of existence. By contemplating such phenomena, we join a timeless human tradition, one that seeks not just to map the stars, but to find meaning in our relationship to the immense, beautiful, and mysterious cosmos we call home. The next leap in understanding will not come from a single telescope, but from a coordinated symphony of new eyes on the cosmos. The James Webb Space Telescope is already rewriting our cosmic maps with its profound infrared vision, seeing through the dust of the Zone of Avoidance to reveal countless galaxies that were once mere phantoms. Each newly spotted island of stars adds a crucial data point, helping us chart the true boundaries of the gravitational well we are flowing toward. Meanwhile, the European Space Agency's Euclid mission has a different, equally vital goal. It will not simply look at galaxies, it will look through them, by meticulously measuring the subtle distortions caused by weak gravitational lensing. Where the gravity of dark matter bends the light from distant galaxies, Euclid will create a mass map of the unseen universe. This is like finally being able to see the contours of the riverbed itself, not just the leaves floating on the surface. On the ground, an endeavor of staggering scale is taking shape. The Square Kilometer Array, a network of radio telescopes spanning 2 continents, will act as a cosmic hydrographic survey. It will detect the faint radio whispers of neutral hydrogen gas, the primary fuel for stars which permeates all galaxies. This will allow it to trace the cosmic structure in regions our optical telescopes cannot reach, painting a complete picture of the hidden filaments that feed the Great Attractor. Together, these missions will provide a flood of data so rich that we will be able to build the first truly dynamic, 3-dimensional model of the entire Attractor region. We will not just see a static snapshot, we will be able to simulate its evolution and understand how it grew to such immense proportions. This collaborative future points toward a profound shift. We are moving from simply finding the source of the pull to comprehending its intricate mechanics. The mystery of the Great Attractor is not a wall, but a doorway. With every new technological window we open, we step closer to a universe whose hidden architecture is slowly, beautifully, being brought into the light. These digital universes are born from pure mathematics and raw computational power. Inside the world's most advanced supercomputers, scientists program the fundamental laws of physics, feed in the known initial conditions of the Big Bang, and then press play. Over millions of processor hours, these simulations calculate the gravitational dance of trillions of particles of dark matter and gas, watching as they coalesce into a virtual cosmos that evolves over billions of simulated years. The result is a breathtakingly detailed map of a fictional universe, a parallel reality governed by our best theories, and in these digital realms, something remarkable and deeply validating happens. Great attractors do not need to be programmed in. They emerge spontaneously from the chaos, forming as natural gravitational anchors at the intersections of the cosmic web's densest filaments. This is a powerful confirmation that our underlying model of the universe is essentially correct. Projects with names like the Millennium Simulation and Illustris TNG have become virtual laboratories for cosmology. Researchers can step inside these digital realms and perform experiments that are impossible in the real universe. They can track the precise trajectory of every single virtual galaxy, measuring its flow toward the simulated attractors. They can then compare this river of digital motion to the real flow we observe from Earth, checking for a match. If the simulated galaxies move too fast or too slow, it suggests our theories about the amount of dark matter or the nature of gravity need tweaking. It is a process of cosmic calibration, refining the recipe for our universe until the virtual and the real align. One of the most profound capabilities of this approach is the power to rewind time. In the real world, we see only a single snapshot, the present-day arrangement of galaxies, but in a simulation, astronomers can run the clock backward. They can trace the path of a virtual Milky Way, following its winding journey over billions of years to see which gravitational wells it has been drawn toward in the past. This allows them to test different histories for our own galaxy, piecing together the long-forgotten chapters of our cosmic voyage. Without these immense computational models, the Great Attractor would remain a static mystery. The simulations breathe life into the data, transforming a single moment of observation into a dynamic, evolving story. They reveal that the attractor is not a fixed point, but a living structure, one that has grown and shifted over the eons, its influence waxing and waning as the universe expands and new structures form around it. This digital universe is our guide, a shadow reality that helps us interpret the faint signals we receive from the depths of space, turning the silent pull of gravity into a narrative we can finally understand. The space between galaxies is not a perfect void. It is filled with a whisper-thin gas known as the intergalactic medium, a substance so diffuse it would be considered an ultra-high-grade vacuum in any laboratory on Earth. Yet across cosmic volumes, this gas becomes a major player, a hidden ocean whose currents are steered by the same immense gravity that pulls on the stars. Within the heart of the Great Attractor, this intergalactic medium undergoes a dramatic transformation. As vast clouds of gas are drawn into the deep gravitational well of clusters like Norma, they are compressed and heated to staggering temperatures, reaching millions of degrees. At these extremes, the gas does not glow with visible light. Instead, it shines with intense X-rays, turning the entire region into a brilliant, high-energy beacon. This is more than just a cosmic light show. The X-ray glow acts as a direct measurement of the gravitational potential, a way to weigh the entire system. By analyzing the intensity and distribution of this radiation, astronomers can calculate the total mass holding the hot gas in place, confirming that this searing plasma alone can account for a significant portion of the ordinary, or baryonic, matter in the cluster, adding its own substantial pull to the overall gravitational field. To map this invisible atmosphere with even greater precision, scientists use a subtle cosmic effect. When the faint afterglow of the Big Bang, known as the cosmic microwave background, passes through a cloud of this hot, energetic gas, the electrons within it give the light a slight energy boost. This imprint, called the Sunyaev-Zeldovich effect, allows telescopes to detect the presence and pressure of the gas even in galaxy clusters that are extremely distant or faint. Combining this data with direct X-ray observations creates a comprehensive pressure map of the attractor region, revealing the true density and distribution of this colossal, hot atmosphere. The story of this gas is not static. It flows. Vast rivers of cooler, primordial hydrogen travel along the dark matter filaments of the cosmic web, channeling fresh material directly into the gravitational heart of the attractor. This continuous inflow does more than just add to the cluster's mass. It is the primary fuel for star formation, influencing the evolution of every galaxy caught in the flow. A galaxy's journey through this rich, dense environment can trigger bursts of new star creation or, conversely, strip away its gas reserves, leaving it starved and dormant. The behavior of this intergalactic gas is therefore inextricably linked to the gravitational destiny of the Great Attractor. It is not a passive component. It is a dynamic and responsive element of the cosmic web, its movements and transformations dictated by the same unseen forces that guide the galaxies themselves. By understanding how this gaseous ocean moves and interacts, we move beyond a simple map of mass. We begin to see the living, breathing mechanics of the cosmos, a system where gravity, light, and matter engage in a continuous billion-year dance. Long before we mapped its gravitational pull, humanity sensed the presence of unseen forces guiding our destiny. Ancient cultures looked to the heavens and saw not random stars, but a celestial blueprint, a grand design where the movements of planets and constellations directly shaped the fates of individuals and empires. They understood a fundamental truth we have only recently quantified, that there are patterns and powers in the cosmos far beyond our control. The Great Attractor, in its silent, relentless pull, is the modern embodiment of this age-old intuition. It is the scientific validation of a mythological concept, the hidden hand that tugs at the threads of existence from the depths of space. This idea of a predetermined cosmic path appears in countless cultural narratives. The Greeks spoke of the Moirai, the three fates who spun, measured, and cut the thread of life for every mortal, their decisions absolute and inescapable. Norse mythology described the Norns, who carved runes into the world tree Yggdrasil, dictating the laws and outcomes for all beings. In these stories, just as with the Great Attractor, individuals move through their lives largely unaware of the vast, impersonal machinery guiding their journey. Our galaxy does not choose its path, it simply follows the gravitational current laid out for it, a leaf on a river whose source it cannot see. In modern times, this cosmic mystery has ignited the imagination of artists and writers, becoming a powerful motif for the unknown. Science fiction authors have woven tales around enigmatic celestial objects with irresistible gravitational pulls, places that draw explorers toward profound truths or surprising revelations. Visual artists create stunning renderings of swirling galaxies caught in luminous filaments, all flowing toward a dark, central point, a visual metaphor for the universal human experience of being drawn toward something we cannot fully comprehend. The Great Attractor serves as a blank canvas upon which we project our deepest questions about fate, curiosity, and the ultimate destination of all things. This symbolic connection reveals something essential about our pursuit of knowledge. Scientific discoveries do not exist in a vacuum, separate from the human experience. They are instead often the latest expressions of our most enduring concerns. We have always looked to the sky and wondered who or what is in charge. The Great Attractor answers that question not with a deity, but with the elegant, indifferent force of gravity. It shows us that the universe is structured, that our journey has a direction, and that we are part of a story much larger than our own. By viewing this gravitational anomaly through both a scientific and a cultural lens, we see its true significance. It is more than a cluster of galaxies. It is a bridge between data and meaning. It connects the cold equations of physics to the warm, enduring human drive to find our place in the cosmos. The pull we feel is not just on our galaxy, but on our very imagination, compelling us to look up and contemplate the hidden patterns that have guided storytellers and scientists alike for millennia. What other silent forces might be shaping our collective story, waiting for the right moment to be revealed? This cosmic mystery is not locked away in research papers. It has become a vibrant gateway for anyone to step into the world of astronomy. The Great Attractor offers a perfect, tangible story to explain the invisible forces sculpting our universe, making abstract concepts like dark matter and cosmic flow suddenly feel real and immediate. In planetariums around the world, domed ceilings transform into portals, visually transporting audiences across millions of light years to fly through the cosmic web and witness the grand river of galaxies flowing toward this hidden anchor. Documentaries weave together stunning visualizations and the human drama of discovery, turning complex science into a compelling narrative of exploration. Interactive websites allow you to zoom through three-dimensional maps of the local universe, tracing the gravitational currents for yourself with a click and a drag. For a student encountering these ideas for the first time, the Attractor is more than a topic. It is an invitation. Hands-on activities in classrooms and museums make the concepts accessible and unforgettable. Imagine a group of students using a simple simulation to model how tiny beads representing galaxies naturally flow into the low points of a stretched elastic sheet, a direct analogy for gravitational wells. Or building a physical model of the cosmic web with strings and beads, visually creating the filaments and nodes that define the largest structures in existence. This kind of active participation transforms passive learning into a personal discovery. The engagement extends even further through citizen science projects. Online platforms invite the public to become real data analysts, sifting through images from massive sky surveys to help classify the shapes of millions of galaxies. Every classification made by a volunteer contributes to the larger map, helping professional astronomers refine their understanding of the cosmic structures that include the Great Attractor. This is not a simulation. It is genuine participation in the scientific process, allowing anyone with curiosity to play a direct role in unraveling the mystery. By sharing this ongoing story, educators do more than teach facts. They ignite a spark of wonder and possibility. A child who learns that our entire galaxy is on a mysterious journey might just be the one who, in a few decades, unlocks the final secret of dark matter. This outreach transforms the Great Attractor from a distant anomaly into a shared human adventure, reminding us that the greatest cosmic mysteries belong to everyone. Our understanding of the cosmos is expanding beyond the limits of light. Modern astronomy is entering a new era, one that listens to the universe as much as it looks at it. This is the age of multi-messenger astronomy, a powerful approach that combines different cosmic signals to build a complete picture of the most energetic events. For a structure like the Great Attractor, which we have primarily studied through the light its stars and gas emit, this new methodology opens up entirely new avenues for investigation. Imagine being able to not only see the attractor but to feel its vibrations and sense its most powerful eruptions. While its steady gravitational pull is mapped through the motions of galaxies, the dynamic events within it could soon be heard. Future observatories may detect the ripples in spacetime created when supermassive black holes at the hearts of its galaxies spiral into one another. These gravitational waves would provide an independent and incredibly precise measurement of the masses involved, a direct way in of the titans at the attractor's core. This would cross-check and refine all the mass estimates we have carefully gathered from watching starlight. At the same time, vast detectors placed deep in Antarctic ice or under the Mediterranean Sea are on the hunt for neutrinos. These ghostly particles, nearly massless and barely interacting with matter, travel across the universe in straight lines, unaffected by magnetic fields. A high-energy neutrino detected from the direction of the Great Attractor would be a direct messenger from the heart of an active galactic nucleus, a supermassive black hole in the process of drawing in matter. It would tell us about the incredible particle acceleration happening there, processes completely hidden from our telescopes. Each of these cosmic messengers tells a different part of the story. Light shows us where things are and what they are made of. Gravitational waves reveal the dynamics of immense masses in motion. Neutrinos provide a direct line to the most powerful engines in the universe. By combining them, we move from a flat picture to a rich, multi-dimensional understanding. The Great Attractor, as one of the most massive complexes in our cosmic neighborhood, is a prime candidate for such a coordinated campaign. It represents a future where radio astronomers, gravitational wave physicists, and particle physicists all work in concert. Their combined data painting a portrait of a hidden giant with a clarity we have never before achieved. This integrated pursuit does more than solve one mystery. It showcases a fundamental shift in how we explore, proving that the deepest secrets of the universe are only revealed when we learn to perceive it with all our senses at once. The immense effort to chart this cosmic river demands a profound investment. We build billion-dollar telescopes in the deserts of Chile and launch sophisticated observatories into the void, all to trace the contours of a force we cannot see. It is natural to wonder about the economic justification for such fundamental research, especially when the direct benefits are not immediately obvious. Yet the history of astronomy is filled with unexpected gifts. The quest to see farther and with greater clarity has consistently spun off technologies that reshape our world. The digital camera in your phone, for instance, owes its existence to the charge-coupled device, a sensor perfected by astronomers to capture the faintest whispers of light from distant galaxies. The advanced data compression algorithms we use to stream video were developed in part to handle the immense flood of information from deep space missions. Even the precise lenses and laser-guided surgery systems used in modern medicine have roots in the drive to build better astronomical instruments. These are not happy accidents. They are the direct result of pushing engineering to its absolute limits in the service of pure curiosity. When we challenge our brightest minds to solve a problem as profound as seeing through the galactic plane, they invent tools that ultimately benefit everyone. The knowledge gained from mapping the Great Attractor is its own form of capital. It fuels our collective imagination, inspiring a new generation of scientists, engineers, and dreamers. A student captivated by the story of this hidden force may be the one who develops the next breakthrough in material science or sustainable energy. The James Webb Space Telescope and the Euclid mission represent not just a cost, but a global investment in our intellectual future. They are monuments to human cooperation, uniting nations in a shared pursuit of understanding. While these endeavors may never turn a direct profit, their value is measured in the expansion of human knowledge and the technological ecosystem they create. The resources dedicated to unraveling this mystery affirm a powerful idea. Some pursuits are valuable not for what they produce, but for the deeper questions they allow us to ask, reminding us that our place in the cosmos is defined as much by our curiosity as by our coordinates. This gravitational mystery has not been confined to scientific journals. It has become fertile ground for storytellers, a cosmic blank slate upon which science fiction writers project our deepest questions. In novels and films, the Great Attractor is often reimagined as something more than a cluster of galaxies. It becomes a celestial siren, a gateway to other dimensions, or a symbolic place for an ancient, incomprehensible intelligence. These narratives take the scientific premise of an immense, hidden force and weave it into tales of exploration and first contact, transforming cold data into the heart of an adventure. A common trope imagines a future expedition finally reaching the Attractor, only to discover it is not a natural structure at all, but a constructed artifact of a long-vanished civilization, a machine built for a purpose we can barely guess. Other stories explore it as a conscious presence, a sleeping entity whose gravitational pull is merely the echo of its dreams, gently guiding cosmic evolution toward an unknown end. These fictional explorations do more than just entertain. They serve as a vital bridge, allowing audiences to engage with complex ideas like dark matter and cosmic flow on an emotional level. When a character grapples with the implications of a predetermined cosmic path, we are invited to contemplate the same forces that guide our own galaxy. This crossover between science and narrative is a powerful tool for public understanding. A viewer might not remember the exact mass of the Norma cluster, but they will remember the story of a ship drawn toward a mysterious light, and in that story, they absorb the essential truth that our universe is filled with invisible, shaping forces. The enduring presence of the Great Attractor in fiction underscores a beautiful symbiosis. Scientific discovery provides the spark for creative wonder, and that creative wonder, in turn, inspires a new generation to look up at the night sky and ask what other hidden marvels are waiting to be found, not just by our telescopes but within our imaginations. The same curiosity that drives us to map the Great Attractor also compels us to ask deeper questions about our place in the universe. As we pour immense resources into building ever more powerful telescopes and launching complex missions, a vital conversation unfolds. How do we balance the profound human drive for discovery with the pressing needs here on Earth? This is not a question with an easy answer, but a necessary dialogue about our priorities as a species. The funds and intellect dedicated to peering into the cosmic dark could be directed towards solving global health challenges, poverty, or environmental restoration. Yet history shows us that the technological innovations born from pure scientific inquiry often cascade into society, yielding medical imaging tools, global communication networks, and data processing advances that benefit everyone. The challenge, then, is to foster a symbiotic relationship where the pursuit of cosmic understanding does not happen in isolation, but contributes to a cycle of innovation that ultimately enriches life on our home planet. This ethical framework extends to the very real possibility of one day finding evidence of life beyond our world. The discovery of even simple microbial organisms on another world would forever alter our self-perception. But what if we encountered a complex, intelligent civilization? The protocols for such a moment are not just scientific, they are deeply ethical. Who speaks for Earth? What message would we choose to send, and what are the potential consequences of making our presence known in a vast and unknown cosmos? International scientific bodies have begun to draft guidelines emphasizing caution, consultation, and a commitment to peaceful exchange. The core principle is one of humility, recognizing that such a discovery would carry cultural and philosophical weight far beyond any single nation's interests. As we look to a future of deeper space exploration, we must also consider our role as stewards. The Moon, Mars, and the pristine environments of icy moons like Europa represent new frontiers, but they are also potential sanctuaries for unique scientific knowledge. The concept of planetary protection urges us to avoid biological contamination, ensuring that we do not unknowingly carry earthly microbes to these worlds, or vice versa, thus preserving their natural states for genuine study. This stewardship also looks ahead to a time when resource gathering in space may become feasible, raising questions about the fair use of celestial materials and the prevention of harmful exploitation before it begins. The cosmos is not a limitless quarry but a shared heritage. This brings us to the collaborative spirit that makes modern astronomy possible. No single country could have built the James Webb Space Telescope or operates the Square Kilometre Array alone. These are monuments to international partnership. The ethical imperative here is to ensure that the data and the benefits flowing from these grand projects are shared openly and equitably across the globe. Engaging researchers from developing nations and incorporating diverse cultural perspectives is not just a matter of fairness. It enriches the science itself, bringing different ways of knowing and problem solving to the table, which leads to more robust and creative outcomes. The greatest cosmic mysteries belong to all of humanity, and their exploration should reflect the full spectrum of human experience. Ultimately, the ethics of cosmic exploration remind us that science is never separate from the society that creates it. Every decision about where to point a telescope, what mission to fund, or how to interpret a discovery is made by people with all our values, biases, and hopes. By consciously weaving ethical reflection into the fabric of our quest for knowledge, we ensure that our journey into the cosmos is not only one of brilliant discovery, but also one of profound wisdom and responsibility. How we choose to explore may tell future generations more about who we were than any distant attractor ever could. The very existence of the Great Attractor raises a profound question about our place in the cosmos. Why does a universe capable of producing conscious observers also contain such immense gravitational anomalies? This line of thinking touches on the Anthropic Principle, a fascinating bridge between cosmology and philosophy. It suggests that the fundamental properties of our universe, from the strength of gravity to the nature of the cosmic web, must be compatible with the eventual emergence of life. If the large-scale structure of the cosmos were even slightly different, we would not be here to ponder it. Imagine a universe where the gravitational pull of structures like the Great Attractor was far stronger. In such a reality, matter might have collapsed into a few ultra-dense clumps long before stable solar systems could form, leaving no time for stars to forge the complex elements essential for life. Conversely, if the cosmic web were much weaker, with only faint gravitational attractors, matter might have remained too diffuse, never coalescing into the galaxies that serve as stellar nurseries. Our universe exists in a delicate balance. The same specific parameters of dark matter and dark energy that allowed the Great Attractor to form over billions of years also created the conditions for galaxies to spin peacefully, for stars to have long, stable lives, and for rocky planets to assemble in habitable zones. This perspective does not imply purposeful design. Instead, it frames our observable universe as one possible configuration among a vast, perhaps infinite, array of possibilities. In most of those other cosmic versions, the parameters would be wrong, and no one would ever gaze up at the stars in wonder. The fact that we find ourselves in a universe with these particular large-scale structures is not a coincidence. It is a necessary condition for our own existence. Investigating the Great Attractor, therefore, is more than just mapping a hidden mass. It is a way of reading the unique cosmic recipe that made our journey possible, adding a deep layer of meaning to our quest to understand the forces that silently guide us through the dark. This grand motion places our own concerns in a new light. The daily challenges and triumphs of our lives unfold on a world that is, in turn, orbiting a star, which is itself moving within a galaxy being pulled toward an unseen destination. When we contemplate the sheer scale of this journey, our individual worries can seem to shrink against the backdrop of an entire galaxy's destiny. This is not to diminish our experiences, but to reframe them. We are not separate from this cosmic flow. We are active participants within it. Our planet, with all its complex life and human history, is a passenger on this immense voyage. Every person you have ever known, every story ever told, has existed aboard this ship sailing through the void, guided by forces we are only just beginning to understand. This perspective can be a profound source of resilience. The same universe that reveals our smallness also reveals our incredible capacity for understanding. We are fleeting, yes, but we are also the part of the cosmos that has become conscious, able to look out and trace the invisible currents that carry us. This ability to ask questions, to build tools that extend our senses, and to piece together the story of our own journey is a remarkable form of empowerment. It connects each of us to a timeless human endeavor. The curiosity that drives an astronomer to map the Great Attractor is the same spark that fuels a child's wonder at the night sky. It is a shared project, one that transcends borders and generations, uniting us in a common quest for meaning. Embracing this cosmic view encourages a mindset of unity and curiosity. It reminds us that beneath all our differences, we are all riding the same galactic current, sharing this temporary, precious moment of awareness in a vast and mysterious universe. This realization does not answer all our questions, but it inspires us to live with a greater sense of wonder, to approach challenges with perspective, and to appreciate the profound beauty of being a conscious part of something so much grander than ourselves. Our journey through the gravitational currents of the cosmos reaffirms that we are part of a story far grander than our daily lives. From its initial detection as a baffling anomaly to our current understanding of it as a major node in the cosmic web, the Great Attractor has taught us that the universe is structured by invisible hands. We have mapped its influence with space telescopes, simulated its origins in supercomputers, and traced its pull across millions of light years, yet the deepest questions remain. The true nature of dark matter, the ultimate fate of cosmic flows, and the full architecture of the unseen continue to be active frontiers of research. This mystery stands as a powerful symbol of the endless pursuit of knowledge, where every discovery does not close a chapter, but opens a door to deeper wonders. Let this exploration rekindle your own sense of awe when you gaze at the night sky. That curiosity is a vital part of the human spirit, the same drive that fuels the scientists and engineers charting our cosmic journey. We invite you to share your own thoughts and questions below, as your perspective adds to this collective voyage of understanding. Subscribe to continue exploring the hidden forces that shape our universe. Remember, you are not just an observer of this story. You are living within it on a planet sailing through an ocean of mystery, guided by the silent, persistent pull of the unknown.